So taking a look at our lecture for Module 9.1, taking a look here at first order systems, higher order systems, and some applications. So as this relates to your textbook, 9.1 covers the frequency response of your first order systems. 9.2 is going to cover the frequency response of your higher order systems, and 9.3 is going to cover the frequency response for different applications that we'll go over. So the first thing that we want to take a look at in this section is system analysis in the frequency domain. So the first thing we really want to know is, what does frequency refer to? So frequency is going to refer to how a system responds to a periodic input. One such example could be a sinusoid. So we may have some input here. It's given as f of t. Looks something like this here. We have f of t plus p is equal to f of t, where p is going to be the period and t is the time in this equation here. So this is a generic equation we might see for a periodic input. So there's many different applications that we might see these periodic inputs in. We'll go over a couple of those as we continue on through the lecture. But one of the most important of these could potentially be AC voltage. So this is sinusoidal, and for common AC frequency of 60 hertz, we can then find our period from that by saying the period is 1 over our frequency there. So period is equal to 1 over 60 seconds. Another application we could see this is rotating unbalanced machinery. This is going to produce some periodic forces on the supporting structures. Internal combustion engines produce periodic torque, and reciprocating pumps produce hydraulic and pneumatic pressures that are also periodic. So there's a couple more applications and a couple examples that we might see. So we move on here. We're going to take a look at the frequency response of first order systems. This corresponds to 9.1 in our textbook. So what we want to do is we can consider a mass of m, and this is going to be subjected to a damping force, CV, and another force we're going to call F of t here. So from that there, we can get the model in a form that looks like this. mv dot plus CV is equal to F of t. Where again, your damping force here is CV, and then your F of t is an external force there, and then you have your mass right there from the model. Now, in a lot of examples, we're going to be given some information that we can utilize this general form for. So they might tell us, like down here, that we have a mass of equal to, in this case, 0.2 kilograms and a C value of 1 in Newton times seconds per meter. And they tell us that the force F of t is going to be the sum of two sinusoidal terms of different frequencies. So in general form, we can write that as F of t is equal to F1 of t plus F2 of t is equal to sine of 15t plus the sine of 60t. Now, if we look at just the sine of 15t and the sine of 60t here, when we're to plot these out, we can see down here in the graphs below, the top graph here, we have our sine of 15t in newtons, and the bottom graph, we have our sine of 60t in newtons. And that's exactly what we would expect to see for a sine graph for 15t versus 60t here. And this is something that you can drop this out in a graphing calculator. We could use MATLAB if you are familiar with it, or any other type of program like that you're used to. Mathematica, Excel can even graph these out, whatever your preferred program is. So now we could solve this model using analytical or computer techniques. So from that, we can obtain a plot for the steady state response, or VSS of t, as shown in this figure down here below. So we look at this figure here. We have our VSS of t over here on our y-axis in meters per second, and we have our time in seconds down here on our x-axis. So we can see this is kind of messy and kind of difficult to interpret. But if we obtain the steady state response by considering each sine term separately, we could better understand the dynamics of this system. Another thing that we're going to deal with in a lot of these problems is complex numbers. So we're going to talk briefly here about the representation of complex numbers. So we can represent a complex number in rectangular form. It says n is equal to x plus our jy, where x is going to be the real part and y is going to be our imaginary part of the complex number. So we can plot this in two different dimensions, with x and with y. So we got x on our horizontal axis and y on our vertical axis. And the way we can think about this is as a two-dimensional vector whose head is at the point xy and tail goes through the origin. It's going to have some magnitude, or magnitude we're going to call here m. And it's also going to have a vector angle that we're going to call phi here. And this is going to be measured counterclockwise from the positive real axis, where again recall our real axis here is going to be our x-axis. And it's going to be in the form that the magnitude and the angle of the number can be calculated from this relationship down here. The absolute value of n is equal to the square root of the sum of the squares of our real and our imaginary components. So this leads us to think about when we have these imaginary components, how do we deal with them when we're squaring them and taking the square root of them? What does that mean? And what that does for us is it gives us some sign convention we need to pay attention to. So now let's take a look at a visual of this here. So we have this complex conjugate here, n is x minus yj. So we have down here a vector representation of the complex numbers. So we can see, just as we described before, we have our horizontal, our x-axis here is our real value, and we have our y-axis as our imaginary value here. And we're measuring our phi angle here off of our real axis. You can see if we were to go down here for this vector, this is going to be a negative phi. See, the tail starts at our origin here. It goes up to the tip of this here, and we can see this is our x and y position right here, x plus our yj right there. Where if we had actual values for our x and y here, we can see on the right-hand graph, we go over 3 in the real direction on our real axis, x-axis here, and we go up to 4 on our y-axis over here, which 4j on our imaginary axis. So now, the thing to think about is we're in a quadrant number 1 up here. What if we were in a different quadrant here? Well, if we're down here, and let's just say we have a negative 2 on our real axis, we go over on the x-axis negative 2, and we go down on our imaginary axis a negative 5 over here. For this, what we can see now, our phi is still measured from our real axis here. So we go all the way around like this to get this angle here. So that's 248 degrees. It's not just this small angle here, it's from this real axis up here. So that's why we have a 248 degrees for our phi value. Let's talk about complex numbers as a function of frequency. So these complex numbers will be a function of frequency, our omega term here. And for example, we can see down here, we have n is equal to negative 2 minus a j5 omega all over 3 plus j4 omega. So this is just an example of a complex number. And our methods for obtaining our magnitude and our angle, same as we saw previously of n, are going to be functions as shown below. So we have these that we can reference back to, and we'll use this in a couple of example problems as well. So you can see the magnitude of n is the square root of the sum of the squares of the numerator and the denominator here in the top one. And our phi is going to be our angle n, which is equal to, in this case here, our numerator, negative 2 minus j omega 5 minus the angle of our denominator down here. So in order to get these angles here, we can take our inverse tangents. Continue looking at some frequency response properties here. So now we're going to talk about our LTI systems, our linear time invariant. So the basic frequency response properties of such systems is summarized down below in this table here. So we can see in this table 9.1.1 from our text, we have the frequency response of stable LTI systems. So I'll reference back to this for a lot of the problems that I'm working on. This table gives us a lot of information that's very useful. One thing that we can note here at the top of the table, it tells us the transfer function Ts with S being replaced by our j omega. And this is what's called our frequency transfer function. So with that j term in there, that lets us know that this transfer function is going to be a complex function of our omega. And it's going to have a magnitude and an angle just as any other complex number would. So if the system is stable, this is going to be a sinusoidal steady state output amplitude over a sinusoidal input amplitude. Where input here is going to be our a sine omega t in general form, and the steady state output is going to be given by b sine of omega t plus our phi. So from this here, we now have the following equations, 1, 2, and 3 as shown below here. So then these are going to be great to reference back to as well as you're solving out some of your homework problems and going through some of the examples in the book. So in notation down here, we have the absolute value of t of j omega and the angle of t j omega here. So this is going to represent our magnitude and our angle for the complex number t of omega j. Now we want to remember here our m is what we're going to refer to as our amplitude ratio or our magnitude ratio. And you'll see that within a lot of the problem statements and examples within the textbook. So now let's go over and take a look at figure 9.1.4 to see the results that are illustrated from this. So this shows the frequency response of a stable linear system. So some keywords within that right there. We can see here's our general form of our input, A sine of omega t. Here's our steady state response over here, our output, B times the sine of omega t plus t. And here is our stable linear system right there, our T of S right there. We have our input and our output. So now we can graph this on our real and imaginary axis over here again. Our real axis is going to be our X, our horizontal axis, and our imaginary is our Y, or our vertical axis here. And our vector here is going to have the magnitude of M, and it's going to have an angle of theta down here, where M is equal to our B over our A, which is also equal to the magnitude of our T of j omega, and our theta is equal to the angle of T of j omega right there. So let's take a look at the frequency response of this example right here in general form. Tau y dot plus y is equal to our f of t. So we consider a linear model having some time constant given to us as tau. So if we have a general form of this here, here is our transfer function. So this is great to reference back to. If we are given a linear model and we can get it down into this form, rearrange and simplify to this form, we know that our transfer function is going to be given by this down here as far as the variables in our linear model. So we have T of S is equal to Y of S over F of S, and our transfer function here is equal to 1 over tau S plus 1. We're talking about the frequency response for this linear model here. We have this table down here, which is again is a great reference for all of these values here. So again, we have our M, we just saw on the previous page. This is going to be equal to Y, magnitude of Y over F is equal to 1 over the square root of 1 plus omega squared, tau squared. We have our angle here, our theta, is equal to the negative inverse tangent of omega t. And our f of t, our input function here, is given by A times the sine of omega t. Our B is equal to A times M, where A is right there from our input function there. And our steady state, YSS of t, is equal to B times the sine of omega t plus our theta value there. So this, again, is a great table to reference back to, and we can get our transfer functions in this general form from any of our linear models that we have, and we can get back into this form here. Oftentimes when we're looking at our results, plotting out some of our functions, it's going to be beneficial to use some logarithmic plots. So typically these are going to be used to plot our frequency response curves. Now there's two basic reasons for using these logarithmic scales. One, the curves of our M and theta versus omega can be sketched a little bit more easily if we're using a logarithmic axis. And this is due to the fact that they enable us to add or subtract the magnitude of plots or simple transfer functions to sketch the plots for a transfer function composed of the product and ratio of simpler ones. So that makes it a little bit easier when we're on that logarithmic scale. So the other reason is that logarithmic scales can also display a wider variation in numerical values due to how they space out our axes. So a couple things as we're going through these problems, a little refresher on our log properties here. If we have the log of x times y, recall this is going to be the log of x plus the log of y. We're dealing with a quotient here, and we have the log of x over y. We have this is equal to the log of x minus the log of y. And if we have the log of x to the n, recall this is n times the log of x. So these are great properties of these logarithmic functions that we need to recall and reference back to as we're solving out some of these problems. Let's take a look at a transfer function of a first order system having a numerator dynamics. So we have here T of S is equal to K times tau 1 times S plus 1 over tau 2 times S plus 1. Now an example of this form is the transfer function for the lead compensator circuit from back in chapter 6. So we can see this down below here. In A we have our circuit diagram over here, and B we have our spring system over here with our damping C here, and we can see there's our X value axis and our Y over here. So we have spring given to us as a K1 constant, and we have a K2 constant over here, and we have our damper by our constant C here. Now this relates over to our circuit diagram. We can see, okay, now here's resistor 1, here's resistor 2, and here is my capacitor there. So we can see how we can relate from our circuit diagram here. So on our circuit diagram, we also have this Vs, or our voltage source, or input voltage over here, and our Vo, or our voltage out, our output voltage over here. So now the transfer function for this circuit here, we can see down below. Our T of S is equal to V naught, our output voltage of S, over V of S here, which is equal to, when we do this out for our circuit, our R1 resistor times R2 times our CS plus our R2 all over R1, R2, CS plus our R1 plus R2. And we can reference back to how we got this from a couple of the previous lectures as well, of how we go from our circuit diagram down into this form for our transfer function. Next, we're going to discuss the frequency response of higher order systems. So we already went through and did first order systems. Now we're going to go to some higher order systems. So the results that we saw in the first section of our textbook, we can extend upon these and expand upon these to a stable, invariant, linear system of any order now for this higher order systems. So the general form of a transfer function, we're talking about these higher order systems, is now given to us by this relationship right here. So you can see this keeps going, and we can keep plugging in depending on what order system we're dealing with here. Where the K in this guy here is going to be a constant real number. Now, our complex number, T of j omega, consists of products and ratios of complex factors such that we have this relationship over here now. So our T of j omega is equal to K, and now you can see how this varies from the one up above here, N1 times our j omega, N2 times j omega, so on and so forth. And the numerator and our denominator is D1 j omega, D2 j omega, so on and so forth. Now, if we're talking about decimal units, then we have down here that our lowercase m omega is given by 20 times the log of the absolute value or magnitude of T times j omega, and we can expand that out to the form down here. So most common transfer functions are given by the following form over here that we've already looked at previously. Our T of S is equal to K times our N1 of S times N2 of S, so on and so forth, over D1 of S, D2 of S, so on and so forth for Ni and Di. So these factors Ni and Di of S usually take the form shown in this table below here, and this table here is referenced back to table 9.2.1 in our textbook for the common factors for the transfer function that we see here. So when we're talking about resonance, we note that the complex roots case differs from the real roots case. So we can see this here in the note that m is given by, our magnitude ratio is given by, m is equal to 1 over the magnitude of 1 minus r squared plus 2 times our damping factor, rj. So this can be rewritten a little bit here as 1 over the square root of the sum of the squares. So we're doing the magnitude of that. So we can say that here is equal to 1 over the square root of 1 minus r squared squared. So we're squaring this portion of it here to get the magnitude, and plus 2 times our damping factor times r squared. So then we're squaring this here. So that's where we're getting these magnitude, is by taking the square root of the sum of the squares. Now this is going to have a max value when our denominator is at a minimum. So we can do this by setting the derivative of the denominator with respect to r equal to 0 to make that a minimum. And that shows that our maximum m, or magnitude ratio, occurs at r is equal to the square root of 1 minus 2 times our damping factor squared, which is then going to correspond to omega is equal to omega sub n times the square root of 1 minus 2 times our damping factor squared. So this frequency is the resonant frequency, omega r. Now for the example of an undamped system, the roots are purely imaginary. So our damping factor is equal to 0, and our resonant frequency is the natural frequency, omega sub n. Now the formulas are going to be summarized here in table 9.22 from our textbook, where this is the frequency response of a second order system here. So we have our transfer function, natural frequency, or omega sub n, our damping ratio, our resonant frequency, and our resonant response shown here by these relationships. We want to ask ourselves now, when does resonance occur? Well, this is going to occur when our input frequency is going to be close to that of our resonant frequency of the system. So now, if the damping is small, our output amplitude will continue to increase until either one of two things happens. One, the linear model is no longer accurate, or two, the system completely fails. So now for the case where phi is going to be near a negative 90 degrees, the velocity, or our x dot, is going to be in phase with the input. And when this occurs, it's going to cause a very large amplitude. Now, some circuit designers can take advantage of this fact, and when they're designing their amplification circuits with a natural frequency close to the frequency of the signal that they're trying to amplify, that's going to be beneficial. So an example of this would be a radio station. Now, opposite to this, when we're talking about structural engineers and designers of structural systems or suspension, they're going to try to avoid resonance because this is going to damage or cause complete catastrophic failure of their system that they're designing. So in the last portion of this lecture, I want to take a look at a couple more examples that illustrate the concepts and applications for frequency response. One of these I want to take a look at here is a neutrally stable case. Now, in reality, all real systems are going to have some damping, but it's going to be instructive and useful for us to do some results for the undamped case here, where we have this equal to 0, C value is equal to 0 here. We set our damping ratio here to 0. And the reason behind this is because mathematically, if we're dealing with an undamped case, it's a lot easier to derive this mathematically. And it gives us some insight into the behavior of many different real systems that only have a small amount of damping. So even though all systems have some damping, if we can say, okay, if we can decrease the amount of damping, how are these going to act? How are these going to react to everything? So that's why it's important that even though it's not completely realistic for a completely undamped case where everything's equal to 0, we can solve them that way in order to give us an idea of how they're going to act when there's a small amount of damping. So we take a look at the application for beating here. We note that we can examine the effects from the forcing function independent of the effects of the initial conditions if we set x of 0 equal to x dot of 0 is equal to 0. So now the result is the forced response. So we can see here x of t is equal to f over k times 1 over 1 minus r squared times our sine omega t minus r times the sine of omega sub nt, where omega is our forcing frequency and omega sub n is our natural frequency. So when our omega, or our forcing frequency, is substantially different than that of our omega sub n, or our natural frequency, the force response consists of a higher frequency oscillation imposed over a lower frequency oscillation. So the forcing frequency is close to the natural frequency. If this occurs here, then R is approximately equal to 1, and the force response can be given or expressed by the following relationship here that we see here for our x of t. The last example we're going to take a look at here for an application is base motion and transmissibility. So we have a mass here, m, shown in the figure down here below. And the motion of this mass is produced by y of t of the base. Now the system shown here is the model for many common displacement isolation systems. A couple assumptions that we'll make. We're going to assume that the mass displacement is x, as we can see right here. And this is going to be measured from the rest position of the mass when y is equal to 0. We also note that our weight mg is canceled by the static spring force. And we can prove this to ourselves. We can do out our free body diagram for this system and take a look at all the individual components. So we end up with here is the force transmitted to the mass by the spring and damper is denoted F of t and is given by this relationship down here. f of t is equal to c times y dot minus x dot plus k times y minus x. So this gives us our general equation of motion here, mx double dot plus cx dot plus kx plus cy dot is equal to cy dot plus our ky. And we know that our transfer function for an equation of motion of this form is given here by x of s over y of s is equal to our cs plus k over ms squared plus our cs plus k. And we can reference this back from 9.35 in our textbook. So again, this would be another great example to do to refresh ourselves on this problem here, where we can take this system that they give us and do out our free body diagram and derive our equations of motion and make sure we get it in this form here. Now, a specific example of when this base excitation is going to occur is we're talking about a vehicle. So we have a car that drives over a rough, bumpy road. So the figure below, what we can see here is this is called a quarter car representation. Where our K, when we're talking about our stiffness here, this is going to be a combination of our tire and suspension stiffness combined. So this gives us that general equation of motion here that we just saw previously of mx double dot plus cx dot plus kx is equal to cy dot plus our ky. So we can see this quarter car model represented down here by the body there. So we have our mass m, spring constant k, our suspension over here, our c value there, and there's our bumpy road and our displacement here off of our datum level represented by y. Now, in reality, our roads are not going to be truly sinusoidal in shape, but we can still use this sinusoidal profile to obtain approximate evaluation of the performance for suspension at various speeds. So we can vary our speed in this model here and just use an approximate sinusoidal shape. But again, the thing to note is this is going to be, again, the quarter car representation. So this is just going to be 1/4. You're going to have 4 of these representing each of your wheel axle suspension systems for the car.